Welcome back everyone. In this lecture, we will actually review the structure theory of sln+1c, and then actually we will define the Chevalley generators, which will be very important in the development of representation theory. So, let us recall. So, let us fix some notations. So, let us denote G by sln+1c. So, this is the Lie algebra that we will be interested in. So, we can actually take the diagonal matrices as H. So, this plays the role of the Cartan algebra. So, this is the diagonal matrices from sln+1c. So, it is basically dou n+1 intersection sln+1c. So, recall dou n+1 is the set of all diagonal matrices. So, now we have the basis for this H. So, this is spanned by, let us denote it by Hi, where I range from 1 to n. So, where the Hi's or the usual standard basis Ei minus Ei plus 1 I plus 1. So, we have this Cartan algebra. So, this we will call it as the Cartan subalgebra of G. So, now with this we can actually define the important subalgebras called n plus and n minus. So, they corresponds to positive and negative roots. So, we will talk about roots in a minute. So, we take this n plus to be the span of all these Eij's, where 1 less than or equal to I less than j less than or equal to n plus 1. So, this n plus corresponds to the upper triangular matrices. So, this corresponds to upper triangular matrices from sln+1c. Similarly, one can define n minus. So, this will corresponds to the lower triangular matrices. So, this is span of Eij, where 1 less than or equal to, so sorry, n plus 1 greater than or equal to I greater than j greater than or equal to 1. So, this is corresponds to lower triangular matrices. Okay. So, if as Lie algebras, so if you know what is solvable Lie algebra, both n plus and n minus, they are solvable. Indeed, they are isomorphic. Okay. So, there is this natural isomorphism which actually takes given A to minus A transpose. So, this defines n plus naturally isomorphic to n minus as Lie algebras. Indeed, they are nilpotent Lie algebras. Okay. So, this actually gives us the triangular decomposition. So, you can write G as n minus direct sum H direct sum n plus. So, this we call it as triangular decomposition. Or this is also called Cartan decomposition. So, this decomposition is very crucial for the representation theory. So, now let us make some important observation about the Lie algebra G. Okay. So, I will make this proportion. So, this is indeed a very trivial proportion, but it is important to note it down. So, note that H is abelian subalgebra of G, and the second statement, this n plus as a Lie algebra generated by the following elements x1 etc. xn as a Lie algebra, where these xi's they are given to be the Chevalley generators of this Lie algebra n plus, okay, for one less than or equal to n. So, these xi's are called actually Chevalley generators. Of course, for this n plus we also have the n minus picture. So, if we take n minus, then this will be generated by some y1 etc. yn as a Lie algebra, where these yi's are just transpose of this ei's, ei I plus 1. So, now if we take this particular I for each I from 1 to n. So, now let us look at the subalgebra generated by x and I, xi and yi. So, let us call it Si. So, this is the Lie subalgebra generated by xi and yi. So, which will be naturally the span of xi, hi and yi, hi and yi, and this is indeed isomorphic to as a Lie algebra SL2C. So, this is 3-dimensional and simple Lie algebra. So, note that in particularly we have the following commutator relation. The bracket xi hi xi will be 2 xi, and the bracket xi yi will give you hi, and then the bracket hi yi is going to give you minus 2y. So, this is the Lie brackets that we have it in this 3-dimensional simple Lie algebra. So, now if we take these xi's and yj's, and if we see how they interact, it is easy to see xi, yj they commute if I is not equal to j. So, indeed all these relations are there for your Lie algebra. So, since G is direct sum of this n plus h and n minus, it is clear that so G is as a Lie algebra generated by these xi and yi for I range from 1 to n. So, note that the bracket xi yi takes care of the hi part. Okay. So, since the bracket xi and yi is nothing but hi, so as a Lie algebra G is generated by xi yi for all I range from 1 to n. Okay, let us verify this. The only thing that we need to verify is if we take n plus, so which is by definition it is a span of Vij, which is the set of all upper triangular matrices, and we claim that that is indeed generated by this x1 etc. xn as Lie algebra. So, for this purpose let us prove only the non-trivial statements. I will leave it to you to check other statements. So, we will prove only 2. So, why 2 is true? So, let us take some basis element. Okay. So, for 1 less than or equal to I less than j, coming from this 1 to n plus 1. So, we can just compute what will be the Eij. So, if you do the computation, it is easy to see that. So, this is going to be the bracket I plus 1 and then I plus 1 I plus 2 and so on, bracket j minus 2 j minus 1 E j minus 1 j. So, one can use induction to prove this. So, basically if we take this right normed lever, so these words are called right normed lever, of course formed in this order. The order in which is taken is E I plus 1, E I plus 1 I plus 2 and so on E j minus 1 j. So, if you take it in this order, the right norm levered. So, then if you take the successive bracket, then you get this E I j. So, for example, let us do this simple calculation. Okay. So, if you take E I plus 2 for example, so this is nothing but E I plus 1 and E I plus 1 I plus 2. So, why this is true? So, basically, so the bracket x y is nothing but E I plus 1 times E I plus 1 I plus 2 minus E I plus 1 I plus 2 times E I plus 1. Then you can easily see that only this part is going to contribute, this part going to vanish. So, you get this is exactly equal to E I plus 2. Okay. So, similar to this you can do the calculation and then see if you take the successive brackets, this right norm levered using these elements E I plus 1 etcetera E j minus 1 j. So, then you get E I j. So, this proves that indeed E I j lies inside this subalgebra generated by x 1 etcetera x n. And since n plus is a Lie subalgebra, that is easy to verify. So, in particularly n plus is equal to the Lie subalgebra generated by x 1 etcetera x n. Similarly, for y 1 etcetera y n you also have this Lie subalgebra generated by them equal to n minus. And for 4 these formulas are easy to verify. For example, if you take h I to be E I minus E I plus 1 I plus 1, then the h I bracket x I it is going to be E I minus E I plus 1 I plus 1 times E I plus 1 minus E I plus 1 times E I minus E I plus 1 I plus 1. Then if you do the calculation, you can see that only these two terms survive. So, that will give you E I plus 1 and then this product will be 0 and then this product is 0 and only this product will survive, that is going to give you minus into minus plus E I plus 1. So, which gives you twice E I plus 1 which is twice x I. So, this tells you that the very first formula is true, the bracket x I h I x I is nothing but 2 x I. Similar to this, you can calculate bracket x h I y I, that is minus 2 y I, and then the bracket x I y I is exactly h I. So, now I will leave it to you to actually check the formula 5 and formula 6 actually comes for free because this bracket x I y I is nothing but h I and h I spans h. So, now let us actually observe about how actually the Cartan subalgebra acts on G. Okay. So, the action of the Cartan. So, H acts on G via the adjoint map. So, let us look at its action. So, basically you have the map from add restricted to H. So, basically sending H to add H. So, this map is actually giving you the action of H on G. So, now with respect to this action you can easily see that. So, each element H in H acts semi-simply or diagonalizably on G. Diagonalizably on G. So, we also use the word semi-simple. And we can actually write down since H is being abelian. So, we can actually make H to act semi-simply. So, in particularly we can talk about simultaneous eigen decomposition, space decomposition. So, in particularly, so we can write G as direct sum of G alpha, alpha coming from H star, where G alpha is the weight space. So, G alpha is nothing but those x in G such that the action of H leaves alpha of Hx for all H in H. And note that so this is just comes for free from the fact that H is being abelian. So, now if you think about it, what root spaces will survive? Those alpha in H star such that G alpha is non-zero. So, then this is going to be exactly equal to the following set. So, this is just 0 union phi, where phi is epsilon I minus epsilon j. So, which is restricted to H, where I and j comes from 1 to n plus 1. So, we have to assume that I not equal to j. Okay. So, let us see that how to think about it. So, what is epsilon I? So, the epsilon I, so these are all the ith diagonal projection. Okay. So, we can define it from dou n plus 1 to C. So, if I take a matrix, diagonal matrix, let us say A1 to A n plus 1, then we can send that to its ith coordinate. So, which is the ith coordinate projection. So, the diagonal matrix A1 to etcetera A n plus 1 sent to A. So, this is a linear form on dou n plus 1, and it is easy to see that dou n plus 1 star actually span by all these epsilon i's. Okay. So, now if we take these elements, we can actually define this restriction to dou n plus 1 star to H star. So, note that H is being a subspace of dou n plus 1. So, we can talk about this restriction. So, then what it is actually, so we can denote it by bar. If I take lambda, then lambda bar is nothing but lambda restricted to H. Now, we can take this epsilon I and then send it to epsilon I restricted to H. Okay. So, those elements only we are talking about here. Indeed, there is a better way of thinking about elements of H star. So, if you think about it, so there is this standard inner product on dou n plus 1 star. Okay. So, dou n plus 1 star is nothing but the span of these epsilon i's, where I range from 1 to n plus 1. So, this has this standard inner product, which actually given by the bracket epsilon I epsilon j to be the canonical delta I j. And whenever you have this inner product, so you can easily see that if you take this particular element epsilon 1 etcetera, the sum of this epsilon i's, epsilon 1 plus etcetera epsilon n plus 1. So, this is going to act as 0 on H star. So, the restriction of this is going to be 0 on H. So, now if we take this particular element and then take its orthogonal complement. So, take this orthogonal, this can be identified with H star. So, can be identified with H star. So, in particularly we will have actually inner product on H star, and we can make this H star as inner product space. So, we will actually define this new basis for H star after this identification. So, define this alpha I to be epsilon I minus epsilon I plus 1 for I range from 1 to n. Okay. So, then it is easy to see that this H star has this alpha I as basis. Okay. And not only that, so if we actually take what will be the inner product between them, so you can easily see that the inner product alpha I alpha j, so which is given using this epsilon I basis. So, this is epsilon I minus epsilon I plus 1 inner product with epsilon j plus 1. So, this is going to be exactly equal to, so it is 2 if I equal to j, and it is exactly minus 1 if I equal to, so let us write it as j equal to I plus 1 or I minus 1 and 0 otherwise. So, one way to remember this using the Dynkin diagram. So, if we take alpha 1 etcetera alpha n as vertices and you put an edge between alpha 1 and alpha I and alpha j if the inner product being minus 1, otherwise you do not put any edge, okay, and there is no edge from alpha I to alpha I. So, in particularly you can see that there is an edge between alpha 1 to alpha 2 and alpha 2 to alpha 3 and so on, alpha n minus 1 to alpha n. So, only if you take some ith vertex alpha I, only the neighboring vertices I plus 1 and I minus 1 and I plus 1, they get edges. Okay. All remaining edges will be actually 0. So, in particularly this is just a path isomorphic to path Pn. So, this is the path graph on n vertices. So, we have this information, basically this inner product encoded in this Dynkin diagram. Anyway, we do not need much information about Dynkin diagrams. So, now we can actually make Sn plus 1 act on this dou n plus 1 star by permuting the coordinates. So, Sn plus 1 acts on dou n plus 1 star, which is the span of this epsilon i's. So, by permuting the coordinates. So, how it acts more explicitly, if you give you some element a 1 epsilon 1 plus etcetera a n plus 1 epsilon n plus 1, and then if you take some sigma from the symmetric group, then it just permutes the coordinates. So, this gives you a 1 epsilon sigma 1 plus etcetera plus a n plus 1 epsilon sigma n plus 1. Okay. So, this is how you have the action of Sn plus 1 on this dou n plus 1 star. So, by permuting the coordinates. And note that, and it is an easy exercise. So, each sigma acts as orthogonal transformation. That means it actually preserves the inner product. So, in particularly, so we have the induced action on the H star, so which is identified with this orthogonal complement of this one dimensional space epsilon 1 plus etcetera epsilon n plus 1. So, you have the action. So, there is this induced action of Sn plus 1 on this H star. So, that is because by definition this is those lambda in dou n plus 1 star such that lambda inner product with this epsilon 1 etc. epsilon n plus 1 is 0. So, now if you take sigma in Sn plus 1 and then lambda here in this space. So, then you can easily see that lambda comma epsilon 1 plus etc. epsilon n plus 1 is being 0. So, now if you apply sigma, then you get sigma lambda comma sigma of epsilon 1 plus etc. epsilon n plus 1. So, now all the coordinates of this vector epsilon 1 etc. epsilon plus 1 that is being 1. So, this sigma actually fixes this coordinate. So, this implies that this is exactly sigma lambda comma epsilon 1 plus etc. epsilon n plus 1. So, this is being 0. So, this implies that sigma lambda is again inside this orthogonal complement. So, this way you get action of Sn plus 1 on this H star. So, indeed you have gone modulo all the fixed vectors. So, it is going to be actually faithful action. So, now so we have this S alpha i's. So, these are the reflections defined on H star. So, how one actually defines these reflections? So, just use the formula S alpha I of lambda for any lambda in H star. So, we define S alpha I lambda to be lambda minus lambda alpha I alpha I. Okay. So, this is going to give us reflection, because if I take S alpha I of alpha I, so that is going to be minus alpha I note that alpha I comma alpha I is nothing but, so alpha I by definition epsilon I minus epsilon I plus 1. So, because of that alpha I comma alpha I is going to be 2. So, this is inner product epsilon I minus epsilon I plus 1 comma epsilon I minus epsilon I plus 1. So, if you do the calculation, you can easily see that this is exactly 2. So, now if you take any lambda which is orthogonal to alpha I, so then you can easily see that S alpha I of lambda is going to be lambda, because this part will become 0. So, this actually tells you that S alpha I actually fixes the line which is spanned by alpha I, and then it actually it fixes the hyperplane which is orthogonal to alpha I, and then it sends alpha I to minus alpha I. So, that means it is a reflection. It is a reflection about this alpha I perp. Okay. So, let us see that how S alpha I indeed acts on this basis. So, if you do the calculation, you can actually easily see that if you apply it on the standard basis of H star. So, you can easily see that S alpha I. So, let us denote it by S I for simplicity. Then S I of this alpha j is going to be alpha j if j is different from I plus 1 and I minus 1. So, that is for sure, and S I of alpha I we already know this is minus alpha I. So, if you write in terms of the epsilon I basis, alpha I is nothing but epsilon I minus epsilon I plus 1. So, then this is going to give you minus epsilon I plus epsilon I plus 1. Okay. So, basically this is minus of epsilon I minus epsilon I plus 1. Now, if I take S I act it on alpha I plus 1, so then that is going to give you So, that is exactly going to give you, because alpha I plus 1 comma alpha I is going to be minus 1. So, this is going to be alpha I plus 1 plus alpha I, which is exactly equal to epsilon I minus epsilon I plus 2. Now, similarly, SI of alpha I minus 1 is going to be epsilon I minus 1 minus epsilon I plus 1. So, from these formulas you can easily see that. So, SI indeed simply switches I and I plus 1. So, SI simply switches epsilon I and epsilon I plus 1. Okay. So, that means SI corresponds to the transposition I plus 1. Okay. So, now if we take this subgroup generated by SI, where I range from 1 to n, inside your GL of H star, then naturally one can identify this with Sn plus 1. Okay. So, this is indeed the isomorphism of these two groups. Okay. That is because Sn plus 1 is indeed generated by transposition I plus 1 as a group. Okay. So, now you can easily see that, I will leave it as exercise, this phi that we have defined already, which is epsilon I minus epsilon j for 1 less than or equal to n plus 1. So, this is indeed exactly equal to this Sn plus 1 acting on this alpha i's. So, that means for each alpha in phi, there exists W in Sn plus 1 and alpha I such that alpha equal to W alpha. Okay. And this phi is invariant under this Sn plus 1. Okay. So, conversely, so if you take W alpha I, conversely, if you take W alpha I, that is going to be in phi for all W in W and I from 1 to n. Okay. So, that is what this statement actually says. Okay. So, using this we can actually define the positive roots and negative roots, and we have the following decomposition of phi. So, phi can be written as phi plus disjoint union minus phi plus, where phi plus is given to be those epsilon I minus epsilon j such that 1 less than or equal to I less than j less than or equal to n plus 1. Okay. So, if you think about it, this epsilon I minus epsilon j in terms of these alpha i's, which are called simple roots. So, these alpha i's we call them simple roots, and this phi will be called set of roots. Okay. And this phi plus will be called positive roots. So, now this epsilon I minus epsilon j is actually indeed given by epsilon I minus epsilon I plus 1 plus epsilon I plus 1 minus epsilon I plus 2 and so on, plus epsilon j minus 1 minus epsilon j. So, this indeed corresponds to this leeward that we wrote it. So, this corresponds to E I plus 1 and this corresponds to E I plus 1 I plus 2 and so on. This is E j minus 1 j. So, basically the successively brackets that we have taken is giving you E I j. So, which corresponds to epsilon I minus epsilon j. So, indeed if you write this epsilon I minus epsilon j, then you are getting alpha I plus alpha j. So, the coefficients of this alpha k's inside this expression, they are all non-negative. So, that is why these roots epsilon I minus epsilon j, they are called positive roots. So, basically what we have proved, we proved that this G can be written as direct sum of these root spaces G alpha coming from phi. So, this can be further broken into direct sum of G alpha coming from phi plus, and then direct sum of G alpha minus alpha, again alpha coming from phi plus. Now, if you think about it, so this is exactly n plus and this is exactly n minus. Okay, I will stop here. So, we will use all these informations in order to develop the representation theory of sln+1. So, we will continue with the representation theory in the next class. Thank you.